Hi, my name is Gabe. I'm a mathematician and a tutor, and I'm excited to dive into some statistics with you. Today's topic will be defining and calculating the expected value of random variables. We will begin by defining the expected value in the context of random variables and provide the general formula it follows. We will wrap up by calculating the expected value of some sample random variables to demonstrate how to put our formula into practice. Let's get started. Now, the easiest way to start thinking about expected values comes from an odd source: the lottery. People play the lottery for a small chance of winning a big payout, but how has the lottery company managed to pay out those winnings? Well, if a person has a small chance of winning a lot of money, what that really means is that most of the time they lose the cost of the ticket. On the other hand, the company running the lotto may have to pay out a big amount of money sometimes, but most of the time they actually make a small amount. In the long run, the company will set the odds in the payout of the lottery to continue to make a little bit of money. Specifically, they will expect over the long run to make money in order to keep running the lottery, which means a person playing the lottery should expect to lose money. We say that the lottery company has a positive expected value, while the player will have a negative expected value. Because of this, buying a lottery ticket is a statistically bad idea. Now, let's formalize the definition of expected values. Definitionally, the expected value of a random variable is the mean value of the random variable. If you think of it in terms of the underlying event that the value describes, it is the average outcome that you would observe over an infinite number of trials. It provides no guarantee for any single trial. In fact, it may often not even be a possible outcome for a single draw of the random variable, but it does provide the long-run average. The basic structure of the expected value is that of a weighted average. In English, we can say that it is equal to the sum over the value times the probability of each individual value. So, how do we say this in math? We start with the random variable capital X, a set of possible values for that random variable x sub I, and a probability distribution function which defines a probability of observing each outcome x sub I. We can then denote the expected value of the random variable x either as e brackets x or mu sub x. The reuse of mu, which is normally used to represent a population mean, should further reinforce the concept that the expected value is the mean of a random variable. This is then equal to the sum over I of xi times the probability of observing xi. Let's break this down term by term. The x sub I term provides the values component of our weighted average. The probability of observing x sub I provides the probability of any value occurring. This is the weighting of each outcome. Finally, the sum over the index I indicates that we are summing over all the possible values of the random variable x. Let's see how this works in practice by putting some numbers on our lottery problem. In order to do this, we need to provide ourselves with a set of possible values and probabilities for the player. For this lottery, let's assume that the possible payouts are $100, $25, and $10. The cost of a ticket is $2, which we will write as a negative $2 return. This lottery also has probabilities associated with each payout. There's a 1% chance of winning the $100 jackpot, a 2% chance of winning $25, and a 2% chance to win $10. That leaves us with a 95% chance of not winning anything. Not great, but the $100 jackpot is not crazily unlikely. Still, before playing, we can ask ourselves what the expected value of the return for the player is, given the possible payouts. According to the formula for the expected value, we need to sum over the values weighted by their probabilities. Using our tabular notation, we can determine the contribution to the sum for each payout by multiplying the value times the probability. Pause the video for a moment to see if you can work out each term. Hopefully that has made sense for you to calculate. These values for each contribution are now calculated in the appropriate row. Now that we have all the individual contributions to the sum, we can simply add these terms up. Doing so, we have that these contributions sum to negative 0.2. Thus, we can say that the expected value of this lottery is negative $0.2 to the player. Of course, this is not a possible outcome of any single game, as it is not on the payout table, but it is an average to be expected over many games. Now, what does this mean for the player over 100 games? Pause the video for a moment to think about this. Well, every time someone plays, they should expect to lose 20 cents. Yes, every 100 tickets or so, the player might get lucky and win $100, but those occasional wins are accounted for in the expected value. Thus, 100 tickets means multiplying the expected value of one ticket by 100, which leads to that person losing $20 over 100 trials. This is the sort of analysis that the expected value lets us do on random variables. While we did not address them here, all important statistical distributions have formulas for their expected values. These formulae are among the most important characteristics of a distribution and are very useful for more involved analyses. Finally, before we go, just one more reminder that it is okay for the value of the expected value to not be part of the possible outcomes of the distribution. This is particularly common with discrete variables like the lottery, which we outlined in our example problem. The expected value is just an average, which you can think about as the average over many trials. It does not have to be, and very rarely is, a number that comes up when performing an individual draw. In summary, this video introduced the concept of the expected value of a random variable, as well as the mean value of that random variable. After introducing that concept, we introduced the formula for the expected value, noting that it acts similarly to a weighted average, and we use this formula to calculate the expected value of a lottery, which, statistically, you always lose. Hopefully this was a helpful introduction to the expected value of a random variable. Be sure to keep track of this idea while studying other topics in statistics related to probability distributions.